Hello everyone, we are presenting our project on the windshield wiper mechanism as part of the Mechanism Sessional course ME29002 at IIT Kharagpur. Our team consists of Pranav Khare, Brajesh Kumar Sahu, myself Isha Singhal and Kunal Chelak. In this project, we focused on designing, analyzing and simulating a 4-bar windshield wiper mechanism that delivers smooth and symmetric wiping motion. In this video, we will briefly walk through the project scope, objective, fundamental criteria like Greshov's law, the kinematic analysis we've performed, our design and development workflow, possible improvements, and the final conclusions. The main objective of our project was to design and simulate a wiper mechanism without any quick return effect, ensuring uniform wiping over the windshield. Our approach had 4 key phases. First, synthesis of linkage. We designed a 4-bar mechanism that gives a symmetric sweep. We tested multiple configurations using linkage software and finalized the dimensions after several iterations. Second, velocity and acceleration analysis. Using vector loop equations, we computed angular position, velocity, and acceleration for a constant motor speed. Third, mechanism simulation. We created an animated model in Fusion 360 and the linkage software. We also plotted velocity and acceleration variations for different driver speeds using MATLAB. Finally, we visualized the wiped region, shading the full area covered by the blade during its motion. To ensure that the mechanism allows continuous rotation of crank, we verified Greshov's law. According to the Greshov's criterion, the sum of the shortest and the longest links must be less than the sum of the remaining two. In our design, S plus L equals 183 millimeters, while P plus Q equals 187 millimeters. Since 183 is less than 187, the mechanism satisfies Greshov's criterion, guaranteeing smooth, continuous motion of the driver link. Okay. With this, I will hand over it to Brajesh, who will now explain the kinematic analysis, starting with the displacement calculations.
Thank you, Isha. Now going further, I would like to explain about the displacement analysis of the mechanism. Our goal here is to relate the input crank angle θ2 to the output link angle θ4. We have taken the general wiper mechanism as it was given in tutorial 2 question number 6 with link lengths as AB equal to L1, BC equal to L2, CD equal to L3, AD equal to L4 with AD being the ground. DE equal to L0 is an extrusion of the link CD which connects the mechanism to the wiper T. Now, the mechanism can be visualized as shown on the right, which is a 4-bar mechanism. Here we have taken A as the origin and we get the corresponding coordinates of B and C as follows. Now we'll apply the loop equation over here and we get the equation as BC square equal to L1 plus L4 cos θ4 minus L2 cos θ2 whole square plus L4 sin θ4 minus L2 sin θ2 whole square. Now solving this equation further and transforming it to the form of A sin θ4 plus B cos θ4 equal to C, where A equal to sin θ2, B equal to cos θ2 minus L1 by L2, C equal to L1 square plus L2 square plus L4 square minus L3 square by 2 L1 L4 minus L1 by L4 cos θ4. Now we'll use the half angle formula where we take sin θ4 equal to 2x by 1 plus x square, cos θ4 equal to 1 minus x square by 1 plus x square, where x is taken as tan theta by 2. Now we'll get a transformed equation as follows: b plus c x square minus 2ax plus c minus b equal to 0. Now solving this equation we get x as follows. Now putting x in the previous equation we'll get the corresponding value of θ4 and θ3. Now going further, I'd like to explain how the velocity analysis, which gives us the relation between input angular velocity and output angular velocity. Now our displacement equation was A sin θ4 plus B cos θ4 equal to C. Now if we differentiate both the sides, we'll get the relationship between θ4 dot and θ2 dot as shown with the help of the Jacobian J. If we further differentiate this equation, we'll get the angular acceleration. Now the value of dou J by dou θ2 and dou J by dou θ4 can be calculated as shown, where the values of A, B, C and A dot, B dot, C dot as given. Now going further, I'd like to analyze about the torque requirement using the principle of virtual work, where the relationship between the input torque and the output torque are related to the same Jacobian J. Now consider a constant load movement, constant because the wiper blade pressed down on the windscreen with almost a constant force at all configuration. Now we apply the virtual work principle to get the relationship between tau 2 and tau 4 as tau 2 equal to Jacobian into tau 4. It's the same kind of relationship between theta 4 dot and theta 2 dot. Now I'd like to conclude my part and hand over the rest of the things to Pranav. Thank you.
Explaining how we designed, analyzed, and simulated our windscreen wiper mechanism. We started with kinematic study of standard wiper mechanisms. Using our kinematics of machines knowledge, we understood the motion requirements and also why the traditional 4-bar wiper has quick return effect. Our aim was to design a mechanism that gives a uniform wiping motion and covers a good swept area. Next, during conceptualization, we experimented with different link lengths and pivot positions. We decided on a symmetric 4-bar configuration because symmetry helps reduce the quick return effect and gives smoother wiping. After finalizing the geometry, we performed kinematic analysis. We derived the loop closure equations for the 4-bar and solved for link positions, velocities and accelerations for the constant motor speed. Then we implemented the complete mechanism in MATLAB, ran the full kinematic simulation and validated our design by checking the wiper tip velocity and acceleration behave over time. Finally, we created the mechanism in Fusion 360 and Linkage, where we did motion studies, checked the swept area and visually verified the motion. This slide shows the overall workflow we used. On the left is our MATLAB code where the full analytical calculations were done. At the center in the linkage software, we tried different link combinations and iteratively tuned our design. This helped us very quickly test ideas and visually observe the wiping pattern. On the right, we built the final mechanism in Fusion 360. Fusion 360 helped us verify that the mechanism is physically realizable, all joints work correctly and the swept area matches our expected range. We first recreated the given model from the tutorial sheet to understand the original motion and the quick return behavior. Then we created our modified model where we changed the geometry, shifted pivots and used symmetric links. This modification clearly improves the wiping uniformity and increases the useful sweep. You will see both simulations side by side in our video. Next, I will explain the MATLAB implementation that I have developed. We begin by defining the geometry of the 4-bar, including the ground link, crank, coupler, rocker, and the extended wiper arm. For each time instant, we calculate the input crank angle and then solve the position analysis using the tan half angle closed form method. This converts the loop closure equation into the quadratic equation. Solving the quadratic equation gives two possible rocker angles and we choose the correct one by checking continuity with previous time step. Once positions are known, we set up and solve the velocity equations to complete the angular velocities of the coupler and rocker. Then we set up the acceleration equations using the tangential and radial components to compute angular acceleration. Using the rocker's motion, we calculate the velocity and acceleration of point C, which is the wiper tip. This is done using standard rigid body relations. We repeat this for different motor speeds, 5 radian per second, 10 radian per second and 20 radian per second. Finally, the velocity and acceleration graphs show how the tip speed increases with input speed but maintains the same motion profile. The peaks and smooth transitions confirm that our redesigned 4-bar mechanism gives reliable and uniform wiping motion without quick return issue. With this, I will hand it over to Kunal, who will explain further.
We started by creating precise 2D sketches for each link based on the actual dimensions we calculated during synthesis. Using core solid modeling tools like Sketch, Extrude, Revolve, and Fillet, we generated clean and accurate 3D profiles of the crank, coupler, follower, and the wiper arm. Once the individual components were ready, we moved to the assembly workspace. Here, revolute joints were primarily used to replicate the real rotational degree of freedom present in the actual wiper mechanism. During assembly, as-built joint helped fix the relative position of the component without altering the geometry. while align constraints were used to ensure perfect coaxial alignment between pivots, especially at the motor shaft, link to link joint, and the base frame. By constraining each link correctly and maintaining realistic mechanism relationships, we ensured that the mechanism behave exactly like the theoretical linkage mechanism system. Coming to the project scope, our current model can be extended in several directions, such as adding dynamic forces, friction effect, and developing a full 3D simulation for more realistic motion analysis. We can also experiment with parallel wiper mechanism, introduce rain-based speed control, and integrate sensor for fully automatic wiper. Now, in terms of applications, this project is highly useful in automotive windshield design and wiper optimization. It helps reduce the need for physical prototypes by enabling virtual testing. It can guide motor sizing, improve efficiency, and also serve as a learning tool for understanding kinematic and mechanism design. Designer can also use it for comparing different configuration and optimizing parameters. Finally, here are some potential improvements we identified. First, an adjustable sweep angle mechanism which would allow tuning the wiping coverage for different vehicle windshield. Second, a smart speed control system using rain or optical sensor to automatically adjust wiping speed. Third, an energy efficient linkage designed to reduce torque peak and increase motor life, especially in electric vehicles. And fourth, a compact foldable wiper arm to reduce aerodynamic drag when not in use. These innovations can significantly enhance safety, efficiency, and adaptability of modern wiper systems. This brings us to the end of our presentation. We hope our approach and result gave you a clear understanding of the wiper mechanism design and analysis. Thank you.